Good evening, everyone. Today I'm going to be talking a little bit about the sympathetic, parasympathetic, somatic nervous systems. And we're going to dive into a lot of detail about the neurons, so I want you to try to stay with me. I'm going to open up my trusty whiteboard here. Let's see how long it takes for that to pull up. But in the meantime, I'm going to start by explaining the autonomic nervous system. So we have our central nervous system, our CNS, which is essentially just our brain right here, our brainstem, and our spinal cord. A very thick spinal cord, mind you. And here's all our vertebrae going all the way down. Beautiful. So the autonomic nervous system, if I had to explain it, is divided between our sympathetic and our parasympathetic. Our sympathetic nervous system, the classic example is the fight or flight response. So when your teacher talks about you getting chased by a bear and your pupils get dilated and you begin breathing fast and all your blood kind of rushes to your core internal organs, that's an example of your sympathetic nervous system at work. The parasympathetic nervous system, on the other hand, is more about resting and relaxing. It'd be kind of like your stomach having a BM when you're laying on the hammock and you're relaxed, you're not worried about anything else. When you're getting chased by a bear, in that classic example, your body isn't so worried about sending blood and oxygen to your lower bowels, to your small intestine, to finish digesting what you have eaten earlier on in the day. And then there's a third one that we want to talk about called the somatic nervous system. Maybe I'll use a bigger marker for this. So we said this is fight or flight. Parasympathetic is more about rest, relaxing muscles. And our third system we're going to talk about here is the somatic, which is just a fancy way of saying voluntary or controlled. So, in a word, yeah, I would say it's about control. Flexing my arm right now is an example of my somatic nervous system at work. Wouldn't that just be my muscular system though if I'm flexing my arm? Well, those muscles are powered by nerves. They require the electrical signals to be sent through the neurons that connect to the muscle fiber itself to contract, kind of like when you hook up a dead frog, to some electrodes and their legs start flailing in the air. That's just sending an electric signal through their nervous system and causing their muscles to spasm. Pretty interesting, right? We're going to get more into that actually when we start talking about ions, specifically calcium. So here we have a sympathetic nervous system. In this nervous system, excuse me, fight or flight. Parasympathetic is about rest, dilation, more specifically. This is about constriction, and somatic is about control. It's about what you voluntarily do. So, as I started with talking about the central nervous system, each of these pathways has a specific origin in or around the brainstem. So, in anatomy, if you've taken that class, you might have learned about the vertebrae, cervical, thoracic, lumbar, and sacral. Well, starting near the top here after those first seven vertebrae that come after the cranium, that might end right here. from thoracic vertebrae 1 through 5, thereabouts, we will have bundles of neurons called nerve, kind of like if you think about your long thoracic nerve that comes down your axillary region. A nerve is essentially just a long string of neurons packaged together. They all kind of propagate that same electrical signal down the pathway. So T1 thoracic, there I was, vertebrae 1 through 5 regarding, where did my marker go? Here it is. Sympathetic nervous system have to do with fight or flight in the lungs as well as the heart. Continuing on from T6, and I'll explain these in a second, just hang tight with me. Through the lumbar vertebrae 1 is about the liver, shaped like this, and the stomach, kind of shaped like this. And then finally, through lumbar vertebrae 2, and actually also lumbar number 1, out of order, but that has to do with the intestines and with the bladder. So given that we're talking about the sympathetic pathway for all of these, our fight and flight response, what do you think is going to happen to our lungs and our heart if we are in a self-defense situation? Well, they're going to start constricting. They're going to start beating faster. Our lungs are going to be contracting at a much faster rate than they are in a rest state. Same thing, kind of like we were talking about earlier with the stomach, the liver, uh, probably the pancreas as well. We're not worried about digesting food or releasing enzymes to store sugar. We're more focused on using the sugar that's already in our system, right? Same thing with digesting and or defecating and urinating. We're not worried about that. And I mean, you might pee your pants the moment that you see the bear, but ultimately that's going to shut down the moment that it really sets into your brain that this is life or death. So regarding parasympathetic now, and I'm going to come back to the way that each of these organs connect to the CNS specifically. But since we're on the subject, we're going to talk about parasympathetic now. So the cervical vertebrae 10 are represented by X. Basically innervates everything from our lungs down to our descending colon. So pretty much all the way down. You might be asking me, Sensei Wit, Shifu Wit, you already had lungs written down over here for the sympathetic pathway. Why is that? Why isn't it just one? Well, that's because most organs, actually pretty much all of them, are innervated by both sides. You don't just want to have an organ innervated by just the parasympathetic or just the sympathetic system. Some may be better innervated by one side than the other, but at the end of the day, you don't want there to only be the possibility of being excited or depressed. You typically don't want your organs to just be one or the other, as we were talking about homeostasis or being in a relaxed state. That's on brand for what we're talking about, this whole unit. And then skipping all the way down to the sacral vertebrae between Numbers 2 and 4, we're going to see our rectum innervated. It's not a great rectum, but it's below the colon, as well as the bladder. Excuse me. There's our little trigoning of the bladder, which is upside down. So here's our parasympathetic rest pathway. We want to be able to relax our lungs. We want to be able to relax everything. It's not just the lungs and the colon, mind you. It's everything between. So from the lungs down to the pancreas, the liver, the kidneys, down to the descending colon, even everything in between. And then past the colon, we're also innervated. Like I said, the bladder and the rectum. We want all of our organs to have the capability to relax, or else that would put a lot of strain on our systems. That's kind of intuitive, right? In each of these pathways, there are two main neurons that propagate action potentials. Hmm. There we go. We have our preganglionic and our postganglionic nerves. For our sympathetic nervous system, we're going to represent them by two roughly equal length neurons, postganglionic. Similarly, we also have two here. I'm drawing it up here because I don't want it to look like they're part of the same pathway. And that postganglionic neuron is going to be really short. It's actually going to be what we call a terminal ganglia, because it's pretty much right on the organ or the effector. If you guys can recall what we were talking about with efferent pathways and effectors, the very first unit. So here's our pre and post. And going back to what I said about these varied vertebrae locations where the neurons actually connect to the spine and go down to the effectors or the organs to receive that signal being sent from the brain, CNS. The ganglion where the neurons meet comes in two varieties when it comes to the sympathetic system. It can be either a chain ganglion, which is just around spinal cord, kind of falls all the way down, one after the other, from T1 to T5 down to L2. You can kind of see why they call it a chain. And each one of these is a neuron branching off of the main spinal cord. And each of them somewhat resemble this figure. It's a rough sketch, but it captures the essence of the principle. So that's the first type of ganglia, the chain ganglia right outside the spinal cord. And then a little farther outside, I'm about to illustrate why I put a little star here. Maybe you picked up on that by the lumbar vertebrae number one, number uno. This is actually an example of what we call a collateral ganglion, specifically in the case of the adrenal medulla on top of the kidneys. You will first see the preganglionic neuron or nerve, right, going into this sort of collateral mass. It's like a spot where these neurons congregate before splitting off to their respective effectors. And the adrenal medulla is kind of the star of the show. Uh, Initiated from L1, going all the way to the top of the kidney. I don't think I have a kidney drawn here. So here's our adrenal medulla, our effector. Now we can release adrenaline. Congratulations. And as I was saying, the postganglionic neuron, in the case of the parasympathetic pathway, is often very short. It's practically right on top of the organ, on top of the effector, to the point where you might as well just have the first neuron. But in any case, we call this a terminal ganglia, where that final neuron connects to something like the bladder or to the rectum, allowing it to relax when the rest of your body is in a relaxed state. So what is going on between these two neurons that we care about that is causing this hullabaloo with these organs in the first place? Let's say that I blow this up and I draw, what type of pathway is this? I'll give you a second. This is parasympathetic because the postganglionic neuron is shorter, has a much shorter trip to reach the effector. Well, the signal being propagated between these two neurons is a chemical one, essentially. And this chemical being released, if I blow this up even more from neuron 1 to neuron 2, is called a neurotransmitter. Because it goes from pre to post ganglion. Anything else that goes from pre to pre, like some sort of reuptake, like we see in serotonin, or even going from post to pre, would be called a neuromodulator. They're still chemicals, they still cause different signals to propagate and be inhibited. But in this specific case, it's a neurotransmitter. Makes sense. So when we want to send a signal from our brain unconsciously, it's not something we can control necessarily. But if our brain recognizes that we're in a relaxed state and it says, okay, we're not running from the bear anymore, now we can poop. In order for the rectum to receive that signal from the brain, essentially chemical will need to be released, and we're going to talk about it in a second, but chemical needs to be released from the brain through the CNS all the way down to S2 to S4, down to these neurons and onto the effector organ that lies just at the end. And it goes pretty fast. Hormones move fast, but electrical signals move even faster. So, in the specific case of the parasympathetic pathway, the neurotransmitter that we're talking about is called acetylcholine. This is all the same chemical. It's being released twice, essentially. And since these neurons release acetylcholine, that would make these receptors on the effector over here, whatever it may be, at least on the parasympathetic path, it would make the receptors here cholinergic, meaning they're activated by acetylcholine. I'm going to tell you also what happens after it's activated, but first let me show you the other pathway, which is sympathetic down here. It's got a little bit of a messed up. This is probably actually more accurate to what it looks like because of all the roots. And we got a nice long postganglionic neuron here. Gorgeous. Acetylcholine, if you can believe it, is still released from the pre-ganglionic nerve, making the receptors on the postganglionic nerve also cholinergic, but also nicotinic. We call them nicotinic because we sort of experimented with them, and apparently nicotine was one of the first chemicals that we tried, and it worked. It received nicotine, thus making it a nicotinic receptor that receives acetylcholine. Just because it receives nicotine doesn't mean it can't receive another chemical also, which is why after getting the jitters from doing some sort of drug or drinking caffeine makes your hand all twitchy. It's really just action potentials going off in your muscles that you can't control. So back to what I was saying about sympathetic pathway. Maybe I can represent this with a different color. Whole different chemical is being released. Ignore that. This one is actually epinephrine, or similarly, norepinephrine, making the receptors on our effector over here in the sympathetic pathway adrenergic, because epinephrine is just another word for adrenaline. So does that make a little bit of sense? Sympathetic pathway is the fight or flight response and is activated by adrenaline. Everyone knows about adrenaline. You get a rush going on the roller coaster or rock climbing. Maybe that's why your muscles get a little shaky as you are nervous climbing to great heights. That's just me riffing. Don't take that as gospel. But yeah, the action after these receptors are activated down each of their respective pathways is either telling the muscle to constrict. We're talking about smooth muscle, blood vessels, cardiac, and even glands, like the sweat glands on your skin, to either relax if it's parasympathetic, as up here, or to lock in, to tense up if it's fight or flight, for lack of a better word. Okay, final subject of the hour. We're going to give mechanisms of action for a bunch of specific types of receptors. Okay, I have a note for this one specifically, so you're going to have to bear with me. But I'm going to talk about excitatory re excitatory synaptic pathways and inhibitory synaptic pathways, essentially. So here we have, okay, I'm going to start with our cholinergic receptors of our parasympathetic pathway. And I'm going to say that of all the receptors that we can see, observe on this effector, it's going to be anywhere from a receptor called M1 to M5, 2, 3, and 4 in between. As for these receptors here, it's going to be alpha 1 to alpha 2, and then beta 1 through 3, and then I think it was delta is what I have written down, delta 1 and 2. As a general rule of thumb, we're going to say that every receptor, not all of them, because it's dangerous to deal in absolutes, the odd numbers coming after a receptor represent excitatory signals, meaning that they essentially propagate what's going on rather than inhibiting it. Which brings me to the next rule of thumb. Even numbered receptors tend to inhibit whatever signal is going through them. They're inhibitory. Let's see here. So let's say that we're sending a signal through our sympathetic pathway here, coming from our T1, let's say, if we want to activate our lungs or our heart here. Signal comes from the brain, goes down the CNS spinal cord, branches off via the chain ganglion, sympathetic chain ganglion, releases acetylcholine at the synapse between the pre and post ganglionic neurons. Excuse me. Signal propagates and adrenaline is released. Hmm, interesting. So if we want to send an adrenaline signal to our heart or lungs, then that's ultimately going to have to do with our alpha 2. Is that right? Oh, excuse me. It's actually B1 or B2. Alpha 2 has to do more with our blood vessels. Beta 1, beta 2, beta 3. Fixed it for you. Beta 2, or beta 1, will have to do with our heart. Beta 2 has to do with our lungs. And this is the exception that I was talking about earlier. This is the one even numbered receptor that is actually inhibitory. So we're sending adrenaline through this pathway. We reach a B1 receptor. And since this is sympathetic, it convinces the muscles to constrict. And B1 excites that signal and it causes the heart to pump to force out blood faster to get to the muscles. Whereas the B2 will inhibit that signal. And our lungs, we don't just want them to constrict, we want them to be able to open. That's just as important because being alive means that your blood is flowing and that you're able to breathe. Okay, moving into more of the specifics. The alpha 1 pathway has to do with the blood vessels. They will also be constricted. This is our excitatory pathway because it's odd. Alpha 2 has to do with our eyes, with our iris. Oh, no. Alpha 1 has to do with our blood vessels, and so does alpha 2. Alpha 1 has to do with the iris. Our iris is going to constrict, therefore making our pupils dilate. Beta 3 has to do with excretion. So you can probably guess what that means. And then we have our delta receptors. D1 has to do with our kidneys, and D2 has to do with brain function. Now let's look at M1 through M5. I'm drawing 5 lines for each of them. M1 has to do with our pupils. Since this is our parasympathetic pathway and causes things to relax or dilate, our iris being affected by M1 is specifically going to be, or sorry, our pupil. We talked about our iris down here. Our pupil is going to dilate because we're relaxed. M2 has to do with our heart rate being an odd number. This is an excitatory pathway, or sorry, an even number. This is our inhibitory pathway. Our heart rate is going to be slowed. For M3, this is going to be for smooth muscle. Odd number is going to be excitatory. Smooth muscles are going to contract more or dilate more, kind of like in the stomach, for example. And then M4 has also to do with the brain, such as like learning, memory, even sleep, a variety of things, as well as M5. Now, each of these different receptors, they will cause a release of a different type of chemical. Alpha 1, M1, M3, M5. All of those are odd numbered, but in that group specifically, they are going to increase the release of a chemical called IP3. Uh, the receptors such as alpha 2, M2, M4, and D2, all these being even numbered, are inhibitory pathways. And they cause a decrease in release of cyclic AMP, which is essentially a form of degraded ATP. And for an increase of CAMP, you will see D1 and B1 through 3 released increase of cyclic AMP. So we really got into the weeds. I'm not sure, maybe I went a little too specific regarding the mechanism of each of these receptors. It's quite a doozy to memorize, but it's easier once you've drawn it and spoken it out loud. But that's essentially all that I had to share for today. Thank you to all who listened, and have a great night. Buenos noches.